Greetings and welcome back. This is really cool. And as I often say in the in-person context of my courses, I find it to be an amazing privilege to have been part of the centuries long string of efforts to try to understand the world around us. And it's just so fun and interesting to report on these deepest of insights. And so, what I'm going to do now, we're in this part of the course that's related to vectors, representations, finding the right coordinates, and so on. And my plan is to talk to you about four different ways of considering the problem of the coupled vibrations of these two masses and three springs. So, as you can see right here, I have mass 1, I have mass 2. They're connected by these three springs. We make the simplifying assumption that the masses in the springs are equal. So the two masses are equal, the three springs are equal in terms of their stiffness. And we ask for the positions as a function of time. That's what we mean by solving a mechanics problem. Now, I'm well aware that, at least ostensibly, this is a part of a course on physical biology. That's great. Of course, I am relatively indifferent to the names of different subdisciplines and feel like if you're attacking biological phenomena such as the transcriptome, that we should bring to bear all the tools we have at our disposal. And one of them is this idea of finding the right coordinates. And what I think is so wild about the subject of normal modes is that it is a special case. It's a special illustration of a much more general point. I still remember exactly where I was sitting during my early days of graduate school when I was a grad student with Anders Carlson. I was sitting outside of the Wayman Crow building on the campus of Washington University. It was a nice day. They had these benches outside of that building, and I unfortunately don't remember the name of the book, but I had found a book that was basically about solid state physics. And before doing the quantized version of this, in order to look at things like the specific heat, it proposed to solve the problem of one-dimensional chains. And I was still very naive, but I was very, very naive at that time and didn't really understand the incredible importance of toy problems in instructing our thinking about very big non-toy problems. And, I think that several examples of that you, the listener, might find interesting to consider is there's a biography of Phil Anderson by Andrew Zangwill. I think it's called Mind Over Matter, and it has a whole series of chapters about Phil Anderson's masterful role of using toy models to elucidate very general things. And then another example is from my colleague and friend Alexei Kitaev at Caltech, and there's a quite interesting interview with him that's online that you can see through, I think, the Simons Foundation, where Alexei talks about the role of toy models in his own research, which has, of course, been very profound. Okay, so that's just to set up the idea. So earlier, I already did a little bit of an analysis of this problem, and so I just want to remind you what I had to say earlier. So using F equals ma, we can write the equations of motion for the two masses. So the left-hand side is the ma part. Ooh, I don't know what happened here. Just bear with me for a sec. I'm hoping it will resume. Yeah. Okay, so on the left-hand side, this is the MA part. And what we have here on the right-hand side, this first term corresponds to the action of this spring on mass 1. This second term considers the action of the second spring on mass 1. You can look at the limits to see that if x2 is greater than x1, that means that spring 2 has been stretched and is pulling the mass to the right. So that's what this thing will say. The force is pointed to the right. Always there's a minus sign here because any motion of x1 past its equilibrium position is going to push to the left. So that's got a minus sign. Here's the equation for the second mass. And as I said earlier, by taking the sum and the difference, we got two ordinary differential equations that we know how to solve, and the solutions to those two equations are something that we can write down basically by inspection. So here they are. So I know that the solution to this equation is, so it's a harmonic oscillator. It's got a stiffness K. That means it has a vibrational frequency given by omega S. And so this is the solution for XS. For XA, I have a similar solution with constants C and D, which allow me to capture the initial conditions. This guy has a vibrational frequency of square root of 3 km. That's cool. Tells us that that mode of vibration is faster. And we can use the initial conditions. What do I mean by the initial conditions? There's 4 of them. I need to tell you what the initial position of the two masses is and what the initial velocities of the two masses are. And if I do that, then I know everything that I need to know. You might note that here these are initial conditions for x1, x2, and dx1 by dt and dx2 by dt. I can get those solutions by basically adding these two. So just as a little piece of arithmetic, I note that x1 is equal to 1/2 xs plus xa, and I note that x2 is 1/2 xs minus xa. So maybe I said that. I don't know. I should check this. So yeah, no, that's right. So if I add these two equations, these two, then I get 2x1. And if I subtract xa from xs, I get 2x2. So that justifies this choice. Okay. So what do I learn from that? I basically can solve for the positions, which I show you here. This is, I guess, I would put this in the category of an exercise for you, the reader. All I'm saying is that you need to decide on your initial conditions, which I've identified here, and then solve for A, B, C, and D. Plug those back into x1 and x2, and this is what will pop out. So what we find is that x1 and x2 of t, they're a mixture of the symmetric, the root k over m terms, and the antisymmetric, that's the root 3k over m guys. And so I can write the positions of any particular initial condition of x1 and x2. I can find the subsequent position, x1 of t and x2 of t, for any choice of initial conditions. That is all buried in these various constants, such as x1, 0, x2, 0, which is the initial position of x1 and x2, v1, 0, and v2, 0, which is the initial velocities of mass 1 and mass 2. And note, if I plot x1 and x2, which I do up here, you see that they're tricky. They're complicated. It's not pure. On the other hand, on the right-hand side, what we're plotting is xs and xa, and you see that they are indifferent to each other in a way. In other words, they're pure motions. And so this is really at the heart, if you like, of the kind of Fourier analysis ideas that I'll be coming back to later. Okay, so what have we accomplished? I think what I've tried to tell you is that here, that for this simple problem, that I can identify a version of collective coordinates. Those collective coordinates here, I'm labeling xs and xa for x symmetric and x antisymmetric. And so then once I know the collective coordinates, they behave independently. So that's the natural variables for this problem. Then if I want, I can go back into the original coordinate system and I can find out what the motions are of the pure x1s and x2s, if that's, for example, what I want to measure with my measuring device. Okay, so that was solution number 1 to the mechanics problem. I think what I would like to do is I would like to just very quickly, and I don't want to belabor this, but I just want to note that I can rewrite this problem, the one that we just did, in matrix form. So, I told you that I liked this idea of unusual vectors. And so let's see, I have minus k1, minus k, plus 2k, 2k, minus k, and then this is acting on x1 of t, x2 of t. Just to see or check ourselves, let's do this matrix multiplication. I get minus k x1, and then plus 2. I'm a little worried that I have got myself off track, so just let me see if I did this earlier so I can save myself the trouble. And yeah, I guess I didn't do that. Okay, so I have to be a little bit more circumspect here. Okay, so what were my equations? Okay, so I don't think what I've written down here is correct. Just by looking at this by inspection, I have md squared by dt squared x1 is equal to minus k, and then times x1, and then plus k x2 minus x1. Yes, so I made a mistake up here, so I apologize for that. Let's redo this. So I think all will be well in a moment. So this is minus 2k, this is k, this is k, and this is minus 2k. And now I propose that we multiply this all out. So I get minus 2k x1 and then plus k x2. For the bottom, I get k x1 and then minus 2k x2. And to see that that's the equivalent of our earlier result, I want to note that I can remind myself of what we had earlier. Let's just look at the x1 case. That was minus k x1, that's the first spring, and then plus k x2 minus x1. That's the stretching of the second spring. And what I note is that that's equivalent to this. Okay. So what have I accomplished by doing this, and why do I bring it up? Because I want us to enter into the world of eigenvectors and eigenvalues, which I think I've already made some comments about this in previous vignettes. But the thing I want to say is that when I've written it in this form, what I can do now is I can assume a trial solution. So x1 of t is equal to x1 naught e to the I omega t. x2 of t is x2 0 e to the I omega t. I recall, or I note, that the second derivative of these guys is going to bring down a minus omega squared. It's going to give us back a x1 0 e to the I omega t. And so if I substitute this trial solution into this guy here, what I'm going to be left with is minus m omega squared, and then x1 0, x2 0, and that's going to be equal to minus 2k, k, k, minus 2k, acting on x1 0, x2 0. In other words, the ei omega t has actually canceled out of the problem, and so what I'm left with is essentially minus 2k plus m omega squared and k and minus 2k plus m omega squared acting on x10, x20 is equal to 0. I can also write this, if I want, as a matrix k minus m omega squared I acting on my 0 vector equals 0. That's a different way of talking about this. So the matrix K in my notation is minus 2K, K, and minus 2K. And I, you already know, is the identity matrix. And the consequence of this, the reason that this is so powerful and so interesting, is that we've turned this original problem of solving two coupled ordinary differential equations into an algebra problem in solving two linear algebraic equations in the two unknowns x10 and x20. And the route to solving these equations is to compute what are called the eigenvalues and the eigenvectors. And I think what I am going to do is just give you a hint of this. And if anybody's super interested in, seeing this in more detail, you can send me a mail, and I will send you the relevant things for you to look at. So here's basically what I'm saying. So this comes from a book that Hernan Garcia and I are working on that's meant to, in a certain sense, cover the waterfront on the subject of transcription. So here's the matrix equation that I just wrote. This is the trial solutions that I just proposed. This is the second derivative, which I just showed you. And that results in this algebraic problem, which is to find the two unknowns, x10 and x20 is one way you can think of it, or alternatively, really to find the frequencies, the m omega squareds, by diagonalizing this matrix. Okay, so this is another way of stating the problem that I just identified, which is I have a matrix times a vector. What it does is produces the vector itself, but multiplied by a scalar. In other words, we're looking for those special directions where the matrix K, when it acts on a vector, it does not change its direction. It only changes its length. That's the so-called eigenvalues and eigenvectors. Here, if you want, you can take a screenshot of this page. All that this is really saying is that the condition for solving this equation was that the determinant of this matrix be 0. We automatically, just by solving a quadratic equation, get this as the determinant. And that's precisely the eigenvalues that we got earlier. Note that omega s, which is the case in which I subtract, so the minus solution, m omega minus squared is equal to 2k minus k, which is just k. And so omega squared is k over m. And then if I keep the plus solution, then I have 2k plus k, which is 3k, and omega plus squared is equal to this vibrational frequency. So that's really quite amazing. And where this leads is that we can then work out what are the two directions, what are the two linear combinations of our original x's that yield those particular eigenvalues. And the answers are what we found earlier just by scratch and sniff. So why did I go through this whole procedure? What was the point of walking us through that whole exercise? The point was that a second way of solving the mechanics problem is to turn it into a problem in eigenvalues and eigenvectors, to turn it into an algebra problem. And the reason that I'm passing through this is because this is now where we're headed in the context of this mechanics problem that takes us and puts us in concrete touch with modern data analysis. So, what am I plotting here? What I'm plotting is the time series over here. What do I mean by the time series? I mean that for every instant in time, there's an x1 of t, and there's an x2 of t. And so what I do is I consider x1 to be the x-coordinate, x2 to be the y-coordinate, and I plot the positions as a function of time. And that leads to this very beautiful pattern for the particular choice of initial conditions. Now what Ernan and I did, and what we proposed to you as the data analysis problem, is let's say that I just show up and I tell you, hey, look on the right. This is the outcome of something I did. I'm not going to tell you what. And there's these two variables, and that's basically a series of data points. In other words, let's say the way that we generated this is to actually sample x1 of t and x2 of t at discrete time and equally spaced time points. And now we plot the points in the xy plane. So that's what that is. And now the question is, what is that data, quote unquote, trying to tell us? Now this becomes sort of a data analysis problem in the spirit of the way data, such as a transcriptome, which is what we will come to shortly, is presented to us in the modern world. And so the thing that I need to say at this point is I need to hearken back to our earlier work on summary statistics. So let's just take a little bit of a detour on that topic. So summary statistics. So if you comb through earlier vignettes, you'll see that there is a vignette which is entitled "Every Distribution Has Its Moments." And just to remind you, the idea that I presented there was this: if I have a continuous probability distribution, then the nth moment is defined as this weighted average. So just for example, mu0 is the normalization condition. That's minus infinity to infinity, x to the 0 power, which is just 1, p of x dx, and that's equal to 1. So that's what I mean by a normalization condition. Mu1 is equal to the mean. That's average x, and that's given by the integral from minus infinity to infinity of x, p of x dx. And mu2 is a measure of the width of the distribution, and it's defined as follows. This is in the case of a continuous distribution. And I can do an analogous set of operations and do that in my Every Distribution Has Its Moments vignette. And the point I'm trying to make is this. So I have some distribution, whatever it may be. And let's say that here's the x-axis, and here's p of x, and let's say that it has some form like this. And I want to report on the nature of that distribution using just a few numbers. So that's called a summary statistic. And in this case, the summary statistic would be, for example, if I offered you two summary statistics. I've done this experiment in classrooms, and in general, people will want to report the mean and the variance as their minimal summary statistics that they're going to permit themselves in order to talk about their distribution of interest. So I now want to generalize that notion of summary statistics, generalize the concept of summary statistic. And the new concept is what we're going to refer to as the covariance matrix. And this is very important to our business of examining higher dimensional data. So recall that we had x1 of t and we had x2 of t. So I have these two variables. It's the positions of the two masses. And what I'm going to mean when I talk about the covariance matrix, in this case, to be very precise, I'm going to define it. That's this 2x2 matrix given by x1 minus x1 quantity squared and averaged. And then I can here put x1 minus x1 average times x2 minus x2 average. And I will copy that and place it down here. And then finally, I have x2 minus x2 average quantity squared. And this matrix, this 2 by 2 matrix, reports on the variance, but in a generalized way. And let's thinking back to our mass spring system. Let me propose for you this situation. So here's K, here's M, here's M, here's K, and there's no spring between them. So would you agree that x1 and x2 are indifferent to each other? In other words, if I compute the average of x1, x2, it will be 0 because they don't talk to each other. There's no sense in which the dynamics of the first mass is coupled to the dynamics of the second mass. But if I now replace this situation with this situation, and I permit myself to add in this spring, then it should be, to me, it's very clear that x1 and x2 are going to exhibit correlated motion, meaning that if I jiggle x1, I'm guaranteed to produce a motion in x2, and therefore this covariance matrix will fire, if you'll let me say it that way. In other words, the off-diagonal elements will be non-zero. So that's where we're headed, and you can actually see from a data analysis perspective, what we're expecting to happen is we're expecting that when we compute the x1, x2, that average, that's going to actually be non-zero, and it will depend on our initial conditions. Like, for example, if I choose the initial motion so that one of them is going to the right and the other one's going to the left, and they're going to oscillate back and forth like this, then their motions are going to be anti-correlated. On the other hand, if I excite the symmetric mode, then their motions are going to be perfectly correlated, etc. So that's the kind of thing that we're after. Now, this becomes very technical, and just in terms of, my personal philosophy, I really believe that for those of you that really care about this, that this is a moment for you to actually go and do the hard work of computing the covariance matrix. What I'm going to do is I'm going to show it to you. For those in my class, I'm not going to assign this as a homework, maybe just for those that are curious as to why it is that I'm doing these videos again, apparently out of the blue, since we're no longer in the pandemic, which induced the original version of this online series of vignettes. There's a few answers to that. So one of the answers is that I am basically now going to try to produce a whole course on physics and biology, but at a level that may be more accessible to a broader audience. But also, there's new things that I've put into the course that I wanted to actually get down on paper, so to speak, but let people see and then comment on, because I think that, even on the 5-year time scale, since I offered the first version of this course online, so much has changed at the level of data analysis. So here's what I'm going to propose right now. I think that this vignette has gone on long enough. So what I'm going to propose is that we stop here, but acknowledging very, very clearly that we're not done. What I've done is I've produced a challenge, and the challenge to us is, how do we think about this data? In other words, it's no longer a mechanics problem. I just show it to us, and I say, here's some data. This is x1, x2 positions or points, and we want to try to understand what we can about the nature of that data. Where we're headed with this is I'm getting ready to now show that this covariance matrix, it will actually have the off-diagonal pieces disappear if we find the right coordinates. And when I say the right coordinates, what I mean is shown right here, in the red curve, which shows you the off-diagonal terms in my covariance matrix as a function of this rotation angle of the coordinate system. In other words, I start out with a bad coordinate system, x1, x2, and I rotate into this new coordinate system, x1 new and x2 new. And what you see is that as we rotate, as we get to the angle pi over 4, or 45 degrees, the off-diagonal terms vanish. And what that means is that I've now found the situation where I've got these two variables which are, once again, independent of each other. They co-vary. They vary separately, I think is the better way to put it. So that's where I am. The proposal is that in the next vignette, which we'll call that part 2, what I'll do is I'll just try to walk you through what the underlying math is. I don't like these things to go on for too long.